All right, everybody, welcome back to now the 7th screencast for this chapter. And we're going to use what we learned in the last screencast about indifference curves and preferred two sets. The beeping in the background, my computer's not about to explode. I live by the post office. There's always big trucks backing up, and I've got the window open. Anyways, we're going to use these indifference curves, and we're going to be able to talk about the preferred two set, and we're going to use the ideal points to talk about something called the Pareto set. In fact, we're going to actually put aside the indifference curves for a little while and just use the ideal points, so just the voters' ideal points, okay? So we're going to start with a new concept for this class, and it's a concept called Pareto optimal, all right? So an alternative is Pareto optimal. An alternative in the space is Pareto optimal if there's no way to move from that alternative without making a voter worse off. In other words, there's no way to move from that alternative without going downhill on someone's utility function. All right. So you are at a Pareto optimal point when there is if you move, you make someone worse off, at least one person worse off. Okay, so here are our ideal points for our three voters, Ted, Marshall, and Barney, on the economic and social dimension. Again, I just put labels on these. You can think of these as just abstract dimension 1 and dimension 2, but here are their ideal points in the space. All right, so here's an alternative Y. Is alternative Y Pareto optimal? All right. Is there any other alternative in the space that at least one of them would prefer and the rest of them would be indifferent? Even better if two of them prefer and one is indifferent. And the best would be, is there an alternative everyone strictly prefers to Y? All right. Well, let's see. All right. So is the alternative Y Pareto optimal? Can we move from Y? Is there another policy in the issue space that at least one of them likes better and everybody else is indifferent? Okay, so let's use our indifference curves to check. All right, so here we go with Y. So first I'm going to put Ted's indifference curve through Y. So Y is pretty far away from Ted. All right, that's a really big indifference curve. Think of it this way. The smaller the indifference curves are, the closer you are to the peak of their utility function. This is really far away. There are lots and lots and lots of things in this issue space that Ted likes better than Y. His preferred two set is all of this stuff, right? And if we can go negative in both directions, it's the entire circle. It's everything inside of the indifference curve. So there's a lot of things Ted prefers to Y. What about Marshall? It's a little bit closer to Marshall's ideal point. It gives Marshall more utility than, say, a point way out here would give Marshall. All right. So Marshall has all of these other alternatives that he's indifferent to Y. Everything inside of the circle is Marshall's preferred two set. There's still a lot of things Marshall prefers to the alternative Y. What about Barney? He looks to be, to me, about the same distance from Y as Marshall, but he is over here in this part of the issue space, and these are all the things that give him the same utility as Y, and everything inside of that indifference curve, all the alternatives inside of the indifference curve, he likes better. They give him more utility. They would map, if we were drawing that utility dimension, onto a higher spot on his utility mountain. So the question in terms of Pareto optimality are there any alternatives that make at least one of them better off without making someone else worse off? All right, and in fact, there are such alternatives. There is a set of alternatives that actually would make all of them better off. It's where all of their preferred two sets overlap, right? It's this lens right here, or petal is what they're sometimes called in spatial voting models. So this petal right here, everything inside of this boundary of these two indifference curves, all three of them prefer. So there's definitely things that make at least one of them better off without making anyone worse off. In fact, there are things that make all three of them better off, all right? For example, this point W, all right? That point makes Ted happier, it makes Barney happier, and it makes Marshall happier. So Y is clearly not Pareto optimal. Right. So Y is one such alternative. In fact, it makes them all better off. All right. All of the alternatives in red make all of them better off. And all of the ones in green make at least one of them better off, sometimes two of them better off. Not all three. All three is the red part. But the green part, notice if I'm moving along this indifference curve, Marshall likes that better and Ted likes that better, but Barney is indifferent. But that's okay. That's still a Pareto improvement over Y. Barney is just as well off. Marshall and Ted are better off. If I move this direction, right, now Barney and Ted are better off. I'm going into their preferred two sets, but I'm moving along Marshall's indifference curve, but that still is a Pareto improvement. It still means that Y is not Pareto optimal, all right? So Y is clearly not Pareto optimal. What about this point Z, all right? Is the alternative Z Pareto optimal? Can we move from Z and make at least one voter better off without making anyone worse off? Sorry about the typo there. I'll try to correct that and re-upload. So is the alternative Z Pareto optimal? All right, let's check again using indifference curves. So here are their indifference curves. I don't know why the dot came up last, but here you go. Here are the indifference curves running through point Z. There are no alternatives that would make at least one of them better off. There are no alternatives that would make at least one of them better off without making someone worse off. Let's see if we can see that without me accidentally clicking and moving to the next slide. So let's try that game we did before where we move along an indifference curve. All right, so I'm here at Z. If I move this way, Ted is unhappy. I have moved not only off of his indifference curve, I didn't move into his Pareto set. I'm sorry, I didn't move into his preferred two set. I moved down his utility mountain. I'm getting further from Ted's ideal point. So even though I'm holding Barney constant and Marshall is getting happier because I'm moving closer to his ideal point, Ted is not happy. So that violates the idea of a Pareto improvement. What if I move in this direction along Barney's indifference curve? Now Ted is getting happier. I'm moving closer to his ideal point, but I'm moving further away from Marshall's ideal point. So Marshall likes that less. That is not a Pareto improvement. All right, what if I move along Ted's indifference curve? Well, now Barney is unhappy. I've moved away from Barney, even though Marshall likes it better and Ted's indifferent. What if I move along Ted's this direction, right? Now Barney is happier, but Marshall is unhappy because I'm moving away from his ideal point. Ted is indifferent to those moves. And you can do the same with moving away from Marshall's. So any direction I move, in fact, if I move this way from Z, Marshall is super happy, but Barney and Ted are both mad now because I'm moving away from their ideal point. I'm moving off of their indifference curve, but not into their preferred two set. I'm moving out of their preferred two set, away from their ideal point. So this is an example of an alternative in the space that is Pareto optimal. There's no way to move from that alternative. So if they were voting, there's nothing that, if it passed, would be a Pareto improvement. Now, things can pass in majority rule that are not Pareto improvements. We're going to talk about that a lot in the next chapter. But there is no other alternative that makes at least one person better off without making someone worse off. So Z is Pareto optimal. All right. So the Pareto set is the set of all alternatives that are Pareto optimal. Another way to say that is the Pareto set is the set of alternatives where there are no Pareto improvements possible, right? That was the case of Z here. Z is in the Pareto set. There are no Pareto improvements possible. I can't move away from it without making at least someone worse off. There's no way to make anyone better off without making someone worse off. So that's the Pareto set, all right? So how do we find the Pareto set? Do we have to check every point in the space? I hope not, because there's an infinity of points in the space. We could do a grid search, right? We could go like every, half unit if we had numbers on these axes and do a grid search and maybe map it out, but we don't need to do that. The Pareto set is actually corresponds to a geometric idea, all right? If preferences are single-peaked and symmetric, and they will be for this class, then the Pareto set has a very nice geometric representation, all right? The Pareto set is defined by what's known in geometry as the convex hull, all right? And it's the convex hull of the ideal points. And the way to think about the convex hull is, say I tied a string around Marshall's ideal point, like these are pegs in a board, and I pull the string around back to Marshall and I pull it tight. It's going to form, for these guys, a little triangle. That's the convex hull. You've got it. That is the Pareto set. So every point on or inside the convex hull is in the Pareto set. So every point on the boundary here, these are what are known as the contract curves between the agents. Every point on those contract curves or inside of the convex hull is Pareto optimal. There's no way to move away from that alternative without making at least someone worse off. The points outside of the Pareto set, there are moves you can make. There are things that would make at least one person happier, all right, without making anyone worse off, all right? So that is the Pareto set. Let me bring back in Z and Y from before so we can see that, in fact, yes, Z is inside the Pareto set and Y is outside of the Pareto set, all right? So that's the Pareto set. It's the set of all alternatives where we can't move away from it without making someone worse off. Outside of the Pareto set, Pareto improvements are possible. We can make at least someone better off without making anyone worse off, all right? So that is the Pareto set.